Okay. Boop.
You signed up for an 8 o'clock class.
Well, I thought I signed up for another one, and then I realized I didn't. I think you have another course. I don't know if you
Not an 88, but yeah, like a later.
something later,
Another course,
and I
yeah.
thought I signed up for it, and I didn't. So I had to crash just to make sure I get the class I need.
Gotcha.
I normally wouldn't do it 8 o'clock class. It's too early.
Very often, yeah. So any questions from homework or quiz or anything? Yeah? So you guys, page 231?
Are you returning back quizzes today or no?
Yes, I did. Or,
Oh, can I have mine?
what's your name?
Getting service quiz.
Yes.
And I gave back some, I turned in some homework too on that day.
I got a little bit of it back. I forgot, hold on. What's that? It'll get back to you.
Huh?
It's coming. So it's at page 231, John. What was it, the number again? 66. So page 231, number 66. So this one says there are 100 centimeters and 1 meter. What fraction of a meter is 20 centimeters? So, would 20 centimeters be a full meter? Would 20 centimeters make a full meter? No. It's 20 centimeters out of what required amount? 100. So you always say, what have I got out of what do I need? So in this case, it'd be 20. I got 20 centimeters out of the 100 that I need. You guys with me so far? Cool. And of course, if I reduce that, then I really see what we already know. I see that that is a fractional part of a meter. It's not a full meter. What do you get when you start reducing this thing? What's really nice, because they both end at 0, I can immediately cancel that 0 out. I can divide both by 10. That's really what that is. And 2 over 10 reduces down to 1/5, because I can divide both by 2. So I got 1/5 of a meter. I can write like that if I want to, or just write 1/5. What it really means is if I have something that's 20 centimeters long, it is 1/5 of a meter long. You guys with me? So that's one major use of fractions, is to see what part of something do I have. Now, of course, if I had, let's say I've got, here's Jeff's part B. If I've got 240 centimeters, then what fractional part of a meter do I have? Well, it's still going to be out of 100. That's how many I need to make a meter. Out of 100, how many do I have? 240. Yeah, 2.4 is one way to write that, or you can just actually, you can reduce it. So you can either say that's 2.4 meters, or you can start to reduce it. All right, divide both of those by 2, and you get 12/5 of a meter. And 12/5 of a meter is better written as in what form for humans? Yeah, so 5 goes into 12 twice with 2 left over. So there's that 2 2/5 right there. Let's see how that kind of goes together, because I know I'm getting a little on myself with decimals, but if you did 240 divided by 100 in your calculator, you get 2.4. Right? Dividing by powers of 10 really just moves the decimal around. Do you see how the decimal just kind of moved there? As I cut it down by 100th. Look at 2/5 real quick. How can I make that out of 10? How do I make 2/5 become out of 10? What would I multiply by? What do I multiply 5 by to get 10? 2. So I've got to multiply the top by the same thing, 4/10. Does anybody know what 0.4 means? As a decimal, what does 0.4 mean? It means 4/10. So 2 2/5 is 2 4/10. Is that cool? Because 2/5 is 4/10 of the same thing, right? If you multiply top and bottom by 2, you get 4/10. How we doing so far? So 2 2/5 is the same thing as 2 4/10. And 4/10 is 0.4. Holy shit, there's the connection, right? This is fractionally. It better be the same dang number as decimal-wise, because they're both coming from the same place. So thank God I do get the same number both ways. Math doesn't care how you represent it. Math just cares that it means the same thing. Right? So math says, cool, you want to put it like that, you want to put it like that, I don't care. All right, so I went a little further than that needed. I'm trying to make connections for later. So what do you need on that problem? That's it. That's all me over there. Okay, good. I just want to make sure everybody understands. Because later I get some, where'd you get that part B, Jack? Where's it? No, I totally made that up. It's me. Any other questions from homework or any other quiz really freaking you out? Did you look that over? Oh, you haven't got yours back. That's freaking out. Yeah, right? Yes. Anybody else not get theirs back? Okay. So no other questions from, yeah.
Can you do
Thank-
4.1 number 25?
So this one's got this 1 whole mile, and they got it broken down 1, 2, 3, 4, 5, 6.
What are you doing?
Is this number 25
I
on
meant
4-1?
45, I'm sorry.
Oh, 45.
Yeah.
Man,
So sorry.
I get all drawn out.
Oh, my goodness.
All right, so 45. So let's see, 33 out of the 50 states contain Indian reservations. So 33 out of 50 states contain Indian reservations. What fraction of the states contain Indian reservations? That's part A. So really, that's really just rewriting the English into math. So whenever I see that phrase out of, 5 out of 6 dentists agree on something. That in English, out of really translates into a fraction, a ratio in mathematics. Right? So how would you write that as a fraction? 33 over 50. So is it 100% of the whole United States? No. Is it more than half of the states? Yeah, because half the states would be 25, and there's 33 of them, more than half. Good.
So that's the same answer for B and C.
Part B says, how many states don't contain Indian reservations? So if 33 do contain them, how many don't? So don't make too much out of this. This is not something to do with the fractions or anything really. This is, if 33 have them, and there's 50 states, how many states don't have them? The rest, right? So what would you do? You do 50 minus 33. Cool. And that would be 20 would be 53. 17. Cool. So that's one way to do it. If it was 53 and 33, that's 20, but it's 3 less, so the answer is 3 less, so it's 17. There's all different ways to kind of play with the numbers in your head to do this. Nobody does these calculations in their head directly normally. They normally have these ways to alter it to make it quicker. So the human calculators, they aren't actually just, they got little tricks that they do to apply to things. I've got a few tricks, but not as many as a freaking human calculator. Part C says, what fraction of the states don't contain Indian reservations? Well, if 17 don't. What fraction 17 out of 50? Cool. Now what do you notice about these two? They better add up to be what? Well, the tops better add up to be 50, but these fractions better add up to be 1. Right? If you add the fractional states that have them and the fractional states that don't, together that makes 1 United States. Sound like a speech, but if we come together. You guys semi with me? And that's really the next section, is doing something like this, adding these. And why is this problem really nice and easy?
Because the lower number is the same.
Exactly. The specific reason why this problem is really easy is because the bottoms are already the same. And I desperately want you to look at it like this. I got 33 50ths. So 33 of something plus 17 of that same thing, of course, is 50 of that thing. Most common mistake I see is somebody will tell me this is 50 out of 100. Now what did that person do? They added the bottoms. And that doesn't really make any sense. If I have 33 of these and 17 of these, I should have 50 of the same things. I should have 50 of those things. I can't have 50 of something else. How the hell did I do that? Okay, cool. Hopeful. So it's really, a lot of the fraction stuff is the same thing as like terms. Now for some of you guys, that doesn't help, because you're like, I still don't get like terms, Jeff. Leave me alone, that didn't help me. But that means you got to go back and get like terms. Like terms should be the thing you build on top of. It's got to be just the basic skill. You got to have that like term idea. If you've got it, then fractions should be that much easier, because they're basically the same idea. Okay, so any other questions from homework or the quiz? Okay, all right. One thing I want to remind you guys, as I'm grading more and more section 3-4s, which is the word problem section, I'm noticing more and more people not really answering the full question. All right, so you'll say x equals 11, but you forgot that there's falcon and pheasant or whatever, and you got to go back and answer both questions, right? You got to tell me what the hell that is. 11, of course, you see me being a complete dork. 11 shoes, 11 light years, right? I know I'm being a dork and I'm doing it on purpose. You got to tell me what the hell it is. It doesn't make any sense by itself. Okay. So, what I want to focus on today. Most of you guys seem to have the basics of solving equations down pretty well. Most of you guys made little mistakes. Some of you guys, I desperately have to come see me. Or see a tutor as much as you can or something. We need those solving equation skills to be there. Because as we keep going forward, we learn about fractions. Guess what's happening in chapter 4? There's a section all about equations with fractions in them. We learn about decimals. Then guess what? There's equations with decimals in them. Right? And then we have equations with everything in them. Oh my God. And then as you go through mathematics, you start learning new functions, and then they show up in equations. Now why would we do that? Because we're evil, you know that. But because in real life, fractions are a part of the problem, so they're going to show up in your equation. In real life, square roots exist, so they're going to show up in your equations. Right? So you got to know how to handle them. If you can't solve equations without any of that crap in it, then you have nothing to build on. Right? So you got to understand the basics of solving equations. Okay, so what I want to focus on today is some group work. And I want to do a little bit of lecture, but then I really want to let you guys loose on doing this. Last time we talked about adding and subtraction, so I want to do a little review. And then I'm going to throw in here multiplying and dividing fractions. And then I've got two parts of this blue book that I want you guys to do. And that's basically what I have planned for today. And then next time we're going to finish out chapter 4. That's the plan. And then we'll take a big old nice week-long break that we desperately need. So when I add fractions, let me give you a nice example. If I had 3/4 plus, what Jeff you can do? 5/4. What would that come out to be? 8/4, which is,
So that can be reduced, can it?
oh yeah, 2. So you don't even, and you could say 2 over 1, which is the same thing as 2, of course. You don't even worry about reducing, really, until the end when you're adding and subtracting. Because you can't reduce right now until you know what the hell you're working with. Right? So you don't even worry about reducing until the end, but you don't forget about it either. Because what sucks is when you got the right answer, basically, but you just didn't put it in the right form. Cool. So what about, who remembers, well, let me give us a little, I gave you like a really heinous problem last time, remember, and I showed you a neat way to do it. Which some of you guys liked, and the rest of you are like, I don't know what the hell is that. But if I gave you something like this, what would you have to do with this? Exactly, because the way to look at this is 7/12 plus 5/6. This is like 7x plus 5y. I can't do that. I can't put those together. The really cool thing, this is not unknowns. These are numbers I know. So I should be able to do more than if they were just variables. So they start with the same idea as like terms. I can't add them the way they are, because they're not like terms. But I can make this the same as that. All right, so if you want to write like this, I don't blame you. So 7/12, what's the LCD going to be between those? The lowest common denominator.
12.
I like the way you're thinking. You're thinking about greatest common divisor. You're thinking about what number goes into both. You got to think the opposite way. What number can they both multiply up to be? Because I can't make this part go down any. I can't reduce this, but I can build this one up. So what number can both these become? 12. And that's kind of a weird way to say it. 12 becomes 12 by staying the same. But you can make 6 become 12. Right? Is that cool? So I leave this one alone, because he's already got 12. What do I do to him to make him have over 12? Yeah, multiply by 2. So I better do the same thing to the top. If I do that, if I do the same thing to the top and bottom, I have the same number. I've just made it look different. So if I multiply by 2, get 12. Multiply by 2 up on top, I get 10. So now I can add them. 7/12 plus 10/12, 17/12. And if I don't say, you can leave it like that. But if I did say, write your answer as a mixed number. Yeah, 12 goes into 17. Once with how much extra left over? 5. So either way of those, if I don't say, you can leave it either way. How does that feel so far? I think most of us should have gone through something like this before. Some of us might be, I still don't understand it, Jeff. But I really want you guys to realize that the bottom line is 5/6 and 10/12 are the same number. So if I have to add 5/6 to something, but it's easier to add 10/12s to that thing, then I can do it, because they're the same number. That's really the fundamental idea here. I'm not changing the numbers at all. 5 divided by 6, if you did it in your calculator, is 0.83333, if I remember correctly. If you do 10 divided by 12, it's 0.83333. They're the same number. So what if I had this one here? Yeah, let's see, John. What do you got? I don't know. Let's see. Yeah. Ooh, yeah, that looks gross. So, one way to tackle this is to start, and this might look familiar to some of you guys. You take the bigger one, and you start writing multiples of it. Has anybody ever done that before? What do I mean by that? I mean 45 times 2 would be 90 times, and then keep adding 45, 135, keep adding 45. So you could do that until you hit a number that you know 25 goes into, and then that's a number they can both become. Do you guys see what I'm saying? Because can I just multiply one of these and make it become the other one?
No.
Not easily. Not by a whole number. That's all I want to use, right? So that's one way to do it, and that's fine. If you know what I'm talking about with this method, you could do that way. And then you can write 25, and you can write a long list of 25s, and then you just wait until they agree on something. Now you can see how that would kind of drive you crazy on some of these problems, because it might take a while for them to agree. So another way to do this, it's sort of like, I can't remember who was doing that earlier. It's like you were doing, or you were doing, when you're looking at the largest number that goes into both, I think it was you. What's the largest number that goes into both 45 and 25? What do you think? 5. Right. How do you write each of these? 5 times what?
9.
5 times 9 for 45. 5 times 5. Good. 5 squared, that's right. 5 times 5 for 25. Cool. And the really nice thing about doing it this way, there's 2 things actually. One, it's a really nice procedure that works always. Right? But you got to kind of know how to break numbers down. You got to know how to factor them. 2, when you get really far along, like in the middle of Math 103 or 110, you're going to start doing fractions with variables on the bottom. Oh, yes. Right? You're going to start adding stuff like 3 over x plus 3 minus 2 over x squared minus 9. That is in your future. And if you just keep this in mind, this process, it works with them as easily as it works with these. Trust me. So a lot of what I do is to try to get you ready for what you're going to have to do later. So if you're used to this process, you'll be ready for that. So now the next step in this process is, what is each one missing that the other dude's got? What's he missing that he's got? Another 5. He's only got 1 5. He's got 2. That's not fair. So we give this guy another 5. And what's he missing? He's got 9. So we give him a 9 to make it all fair. Right? And this is not really here. I broke it up. So is that cool? That's not really there anymore. Because I broke it up. Okay, you guys are semi with me. So what number do I really have on the bottom then? What is 5 times 5 times 9?
25.
225, good. So 225 is on the bottom now. Do you see how that process, I mean, if my goal is to make the bottoms the same, if I break them up and see what they have and give the other one what it's missing, they're going to end up the same, right? You think about what you want to have happen, you think about how can I get there? This to me is the best way to do it, especially when the numbers are kind of gruesome, when you can't see it. I wouldn't do it for this. You could, I mean, here's 2 times 6, so he's missing a 2. Do you guys see that? That's why we multiply him by 2, because he was missing a 2. So what's going to be on the top here? 35. And here? 18. And now that's easy. 35 of these minus 18 of these is how many of those? 17. I love it. Yeah. How can you check yourself? You can actually do 7 divided by 45 minus 2 divided by 25 in your calculator. Somebody help me out. Somebody got the calculator out? Okay, somebody's got it. Where's you? Were you the one with the giant one? You had the giant. You had the giant. But today you get the small one. Okay. So one way you can check this is you take the original problem and you do it in your calculator. And it's going to give you a decimal, right? 7 divided by 45 minus 2 divided by 25 is something. 0.075. 0.075. Blah, blah, blah. Now do 17 divided by 225. They better be the same thing, right? Yeah, they're the same thing, right? Sweet. So that's a way to check this work. You can do what this says mathematically. What does this really say? 7 divided by 45 minus 2 divided by 25. You get some ugly decimal. And then just make sure that your answer here is the same decimal. Then you know that you're right. You know that it worked. Maybe. Okay. So let's talk real quick about multiplying and dividing. And I'm going to unleash you on this group work. So the basic idea is, if I had this is shaded, how would you represent that as a fraction? 1/2, right? Just assume that that actually is half. So this is represented as 1/2. Now if I cut this thing in half again, right, and I take one of those pieces. So if I cut this thing in half, so I basically cut the whole thing in half, and I take this piece, Just if half of that, half of a half, would be 1/4. So cutting the pizza in half and in half again, we all know that makes 4 nice big-ass pieces, right? You fold over and however you want to fold. Right, so that represented mathematically, this would be 1/2 of 1/2. And this of, with percentages and fractions, means multiplying. Here. Half of something is really multiplying it by 1/2. Because what's half of 8? And you would get there mathematically by multiplying here, wouldn't you? 1 times 8 is 8. 2 times 1 is 2. 8 divided by 2 is 4. There's half of 8. Of means multiply with fractions and percentages. For some reason that's being forgotten. I've noticed over the years that less and less students know that. It's so weird to me. It used to be like automatic. 20% of 7. Everybody's 0.2 times 7. There you go, Jeff. Now it's like, I don't know what the hell. But that's what it means. So that's the idea of it. If I cut something in thirds, into 3 pieces, and then I cut each of those in half, I've made little sixths, right? 1/2, 1/3. If I divide by 2 and divide by 3, I'm dividing by 6 total. That's the idea. So to multiply fractions, if I got 1/2 times 1/3, you just multiply straight across. 1 times 1 is 1, 2 times 3, 6. So that's 1/6. And it should kind of make sense. If I have a number less than 1, and I multiply by another number less than 1, the answer is going to be even smaller. 1/3 is small, but then 1/2 of 1/3, that's even freaking smaller. So I get 1/6, which is really small. So if I start throwing in more stuff, 3/4 times 5/7, it's the same basic idea. What do you get on the top? Good. 3 times 5 is 15. 4 times 7 is 28. Cool. Now, where it becomes something where sometimes students don't see why I suggest you do this is when there are kind of big numbers, but they have stuff that are in common. Notice what's going on here. The 3 and the 5 are really in the problem multiplying. They're on the top. What are the 4 and the 7 doing? What are the 4 and the 7 doing to the whole problem? They're dividing, right? Divided by 4, divided by 7, so overall I'm dividing by 28. Cool. So there should be some cancellation I can do. I've got multiplication and I've got division in the same problem. I should be able to cancel if I can. So a nice basic problem with this would be like something like 2/9 times 3/16. Now you could multiply 2 times 3 is 6. 9 times 16 is 144.
Can you cancel out?
But you could first cancel. You can either multiply now and reduce on the second step, or you can reduce now and then multiply what you get. I'd much rather reduce first. Instead of making these big-ass numbers that I got to figure out, how do I break these down? Why figure out how to break them down when they're already kind of broken down? So right here, can I divide 2 and can I reduce 2/9?
No, do it diagonally.
And I can't reduce 3/16. But anything that's on the top can reduce with anything that's on the bottom because on the top is multiply and the bottom is divide. So they should cancel out. So 2 goes into 16, 8. 3 goes into 9, 3. 1 times 1 is 1. 3 times 8 is 24.
Is there another word?
Yeah, now I was about to show you. If you do it just directly, if you do 2 times 3 is 6, 9 times 16 is 144, now you got to reduce this. Well, I know 2 goes into both, don't I? For sure. So 2 divided by 2 divided by 2 would be 3/72. Now here you got to realize that 3 goes into both. Divided by 3 divided by 3, 1 over, incredibly enough, 24. So which way was easier?
The first.
Reducing first was easier, yes.
Does it only apply when multiplying?
So far. We'll get in a minute when it's dividing. You definitely cannot do it when you're adding
And
and
no
subtracting.
subtracting. Okay.
I like that you said that. So if I had the same problem, like this, and I really like that you said that, because this happens all the time the minute we teach this, you start going back to these problems and going, I don't like those numbers. 2 goes into 16, 8, yay, now they're easier numbers. But tell me fundamentally, why was it I was allowed to reduce these? Why could I cancel stuff out? Because this is multiplication and this is division. Now I've got division and I've got addition. I don't have multiplication. Can it cancel? Hell no. Right? So if you try to cancel stuff out, you better make sure you have opposite operations. I do not. I have addition and division. It's not going to do anything. Here I'd have to just get LCD and move forward. Right? Cool. So what about division? I like it. And why? Here's one reason why. In fact, here's the most direct reason why. If I had 3 divided by 1/2.
You put a 1 under the 3.
Say again?
You put a 1 underneath the 3.
You could, yeah. So you could make this 3/1 divided by 1/2. I like it. But let me show you something real quick. Do not do it this way. You could write this as 3 divided by 1/2, could you not? Would you want to? And I don't blame you. Why is that disgusting? Because there's a fraction inside of a fraction, Jeff. And this is like the Russian dolls. Right? Inside. Some of you guys know what I'm talking about. Now here's the cool thing. I don't like that fraction on the bottom. So what would I multiply it by to make it go away? What would I multiply 1 divided by 2 by to make it not a fraction anymore? I would multiply by 2. Wouldn't I make the 2 go away? Whatever I do to the bottom of a fraction, I better do to the top. So that goes away. So what happened then? 3 divided by 1/2 became 3 times 2. 6.
Can't you also do like 3 times 2?
Exactly. That's why I'm trying to explain why it works. So this is why it works. You should never just accept something on the face. I mean, it's a very simple procedure, but you should be like, why the hell do I do that? I've never done that before. Actually, you have. You just didn't realize it. If I did, so what really happened here is whenever I have something divided by a fraction, I can make that become 3 times the reciprocal. And that word reciprocal just means flip. Do I really need that over 1? No. So I could just make that 3 times 2 is 6 like we got there. Cool. Okay. And we've done this before, to tell you honestly. 8 divided by 4 is 2. I love it. But according to this rule, I should be able to write this as 8 times 1/4. And sure enough, 4 goes into 8. It goes into 8 twice, no matter where the hell you put the damn thing, right? So the rule, we've already kind of used the rule before. So, let me do one last problem with you. This is old news for most of you guys, but some of you guys I want on the same page. So most of these are going to be kind of obvious, that I've tried to load it with stuff you can reduce. But the biggest mistake I see is people start to try to reduce right now. I don't have opposite operations yet. I have division and division. That's not going to go anywhere. So the first thing I do is what? No, I'm not adding, subtracting. So I don't have to get like and honors. It's a really good point. When I multiply, I don't need like terms. I can't fully explain that because we haven't talked about exponents truly, but we've talked about it a little bit. Anybody know what x times x is? X squared. Exactly. Remember the exponents that just keep track of how many I multiply? Can I multiply x squared times x? The answer is, of course I can. How many x's do I have now? 3. So it would be x to the 3rd. Can I add x squared and x? The correct answer there is hell no. I'll accept no also. So do I need like terms when I'm multiplying, dividing? No. I need it when I'm adding, subtracting. So you only need LCD when you add or subtract fractions. You do not need them when you're multiplying. Because LCD would be building things up. What am I trying to do when I'm dividing and multiplying? I'm trying to bring things down. I'm trying to reduce. So if you do LCD, you're going to go in the opposite direction. So what's the very first step here, though? Yeah, multiply by their simple. So it's become 15 over 49 times,
7 over 30.
and now you start to look. What goes into both of these? Even more. Yeah, 15 goes into that once, goes into that twice. What goes into both of these? 7. 7 goes into that 7, into that 11. So now I got 1 times 11, 11, 7 times 2, 14, 11. Okay. Some of you guys are falling asleep, I understand. So what I want you to do is in the blue book, you can work alone or work with somebody else. Do on page 69, do the even ones. And page 75, the even ones. Anybody else need a copy of the? I'll have a few, so. 69 and 75, the evens from both.
What?
Oh, let's see.
67. What did you get?
Divided by 2, that's 2.
Huh? I mean, 69, right?
Yeah. Give back the
And 75.
The only reason, the only time this is if you get a 99, you should still do it. Is everybody clear on the assignments? 69 and 75 evens. Work with somebody else, call me over.